right, so chapter 4 is all about ways that we can use derivatives to answer questions to solve problems. So how can we use everything that we learned in chapter 3? So I have this quote from your book. What has always distinguished calculus from algebra is its ability to deal with variables that change over time. So think about this formula here for the volume of a sphere. You learned that back in geometry, maybe in Algebra 1 or Algebra 2. You learned to rearrange it to solve it for r instead of solving it for v. You learned how if you could use different values of r and the value for v that comes out is going to be different. But you've never actually solved a problem about a sphere whose volume was actively changing. That's what calculus can help us do. So imagine I'm blowing a soap bubble. That's not me. Imagine somebody's blowing up a soap bubble or blowing a balloon. And you think about the volume, it's getting bigger because the balloon or the bubble is getting bigger, so the volume must be increasing. So you might like to know how fast that volume is changing, and we can answer that question using related rates. Related rates questions are really an application, just an application of implicit differentiation. So you can remember everything we learned about implicit differentiation, and of course at 3.7 or 3.8, and we're going to use that in a context instead of out of a context. In chapter 3, we had no context. We were just learning how to crunch the numbers. In chapter 4, we have a context, which we're going to use to inspire us to perform an implicit differentiation problem. Okay, so quick reminder about implicit differentiation. This is what you already knew. This is what we did in chapter 3. If I had this equation, y squared plus x squared equals 17, I can't isolate y so that I could take the derivative because this isn't a function. This isn't one-to-one. It's not a function. It doesn't pass the vertical line test. But we can differentiate both sides with respect to any variable you want, but in this case, x. And we can isolate the dy dx term and find the slope of the curve at any point. So this is just a quick reminder of what we already knew how to do. I knew how to start with this, take the derivative of both sides with respect to x, and then isolate the dy dx to get the slope. Implicit differentiation because y was not already isolated when I took the derivative. So just imagine I did that same thing, but I used different variables. I put them here next to each other so you can kind of compare them. But if instead of y squared plus x squared equals 17, I started out with p squared plus t squared equals 17. Same idea, I can take the derivative of both sides with respect to time, or t. Most of the time in chapter 4, it's going to be time. Take the derivative of both sides with respect to t, isolate dp dt. The calculus and the algebra is the same, but the variables are different. So that's the technique we're going to apply to a related rates problem. So go back to the soap bubble. We know about the formula for the volume of, let's assume for discussion that this is a sphere. The rate at which the volume of the sphere is changing is, the volume is changing as time goes by. So the rate at which the volume is increasing is the rate of change of the volume with respect to time. And in derivative notation, we would write dv dt. So if I want to know how fast the volume of that sphere is changing with respect to time, I'm going to take the derivative of both sides of this equation with respect to time. Now in this case, v already happens to be isolated, so I don't have to do any extra algebra to isolate my dv dt. But notice what happens. I'm taking the derivative of both sides with respect to time, but notice that this is not a function of time, it's a function of r, which is why I'm going to have to use implicit differentiation. I'm going to take the derivative of 4/3 pi r cubed with respect to r, which is 4/3 times 3 times pi times r squared, and the 3's cancel. And then multiply by that missing piece of the chain rule, right? So to take it from being in terms of r to being in terms of the variable I want, which is time. So that's where this extra multiplier comes by. That's where this extra multiplier comes from. Okay, so notice that this formula I have now for the rate of change of volume with respect to time, which is called dv dt, has the radius in it, r, and also has dr dt. Well, dr dt means the rate at which the radius is changing with respect to time. So the rate at which the volume is changing is related to, it's a function of the rate at which the radius is changing. So since that's where this name related rates comes from. We've written an equation where the rate at which one thing changes is related to the rate at which something else changes. Now I can use this formula I have for dv dt, the rate at which the volume is changing with respect to time, in order to answer questions about how that volume is changing. If I want to evaluate dv dt, notice I'm going to need to know something about r and the rate at which r is changing. Those are both variables that are in my formula for dv dt. So if you're going to have to be able to say something about dv dt, like on the AP test, you'll have to have some information about both of those things. So if we did happen to know that the radius was increasing at 0.1 centimeters per second, well, the radius is increasing. That tells me about how the radius is changing over time. So that is dr dt. And if at some exact moment, that same exact moment, the radius is 10 centimeters, then I can use those values in my formula. So here I have, let's change colors. dv dt was supposed to be 4 times pi times r squared. So 4 times pi times 10 centimeters squared times dr dt. Well, we said that this is dr dt, so 0.1 centimeters per second. I left the units on there. Obviously, you don't have to leave units on when you're just performing a calculation, but to show you that the units work out, the units make sense at the end. So if I take 10 centimeters and square that, I get 100 centimeters squared. I'm going to multiply that by centimeters over seconds. So that's centimeters squared times centimeters to make centimeters cubed divided by seconds, which makes centimeters cubed per second. And notice that matches this sort of fraction-looking derivative notation. Volume, in this case, is measured in cubic centimeters. Time is measured in seconds. So the rate at which the volume is changing with respect to time is measured in cubic centimeters per second. Right. I strongly recommend the steps that your book uses, that your book suggests. I've written them here. The language is a little bit different on this slide than it is in your notes, but I think you'll get the idea. We're going to start by writing down what we know and what we're looking for. I strongly recommend making a picture anytime there's geometry involved, which is kind of a lot of the time for a related rates problem. What we want to do then, once we have a picture, is to write an equation that relates the variables. And here I'll just specify the variables. The variables that you happen to know rates of change for, but you don't need to write an equation that relates the rates of change. So in that last problem, I wanted to know something about the rate at which the volume was changing, and I knew something about the rate at which the radius was changing. I don't need to be able to jump right to an equation that relates dv dt to dr dt. But if I could go back up one step and relate volume to radius, that's what I need to do. Then I'm going to use implicit differentiation to write an equation where the rates of change are related. I'm going to differentiate both sides then, usually with respect to time, but it could be some other variable. And then we're going to, at that moment, we're going to freeze the picture, and we'll have other information that we can plug in and use that information then to write an equation that contains the thing we're looking for as the only variable that's left. And we're going to isolate that. And then step 6, to interpret in the context of the problem. All right, so let's try this. An example from your book. So we'll stick with spheres for now, not too bad. A spherical balloon is being inflated at a rate of 100 pi cubic feet per minute. So I'm going to look there and I notice cubic feet per minute. Cubic feet sounds like a measure for volume. Per minute sounds like volume over time. So this is probably going to be a question about the rate of change of volume with respect to time. How fast is the balloon's radius increasing at the instant when the radius is 5 feet? The second question, how fast is the surface area increasing at that instant? Okay, so what I know going in, I've been told that this is true about the balloon, and that's the rate at which the volume is changing per time. So with respect to time. So they haven't actually used the word volume. So it's our job to sort of think about what's going on here. If you were inflating a balloon, what about is changing? Well, the volume is changing. The radius is probably changing. So here, this one that they've given us is dv dt. So we know dv dt. And so for question A, how fast is the balloon's radius increasing? So the rate at which the radius is increasing at some time, that's going to be the derivative of the radius with respect to time, so dr dt. So I've written down a note. We need to figure out dr dt. So my next step is to think about not how necessarily dv dt is related to dr dt, but think of any way that I can to relate v and r. Well, that's supposed to be the easy part here. We know a formula for a sphere. We've been told the balloon is spherical. We know a formula for the volume of a sphere that contains r as its variable. So that's what we're going to use. V is 4/3 pi r cubed. Now I'm going to take the derivative of both sides with respect to time. Notice these both have the same with respect to, so that's good. If those didn't match, we'd have to stop and do some thinking. So here I have dv dt is the same. We've already taken the derivative of the volume of a sphere with respect to time. Let me get this. Question is, how fast is the balloon's radius increasing at the instant when the radius is 5 feet? So imagine a teeny tiny balloon getting blown up. Its radius starts small and it's getting bigger and bigger and bigger and bigger. So at the exact moment when the radius of the balloon is 5 feet, I'm going to freeze the picture. So now I'm not going to be finding dv dt anymore. I'm going to be finding dv dt at the time when r equals 5 feet. So let me do this. I'm going to freeze the picture and I'm going to take that equation that I had, which relates the two rates, and I'm going to replace, here's 4 pi r squared. Oh, so here's what I know. I know dv dt is 100 pi cubic feet per minute. So I've replaced dv dt with 100 pi cubic feet per minute. And on the other side, I have 4 times pi. This is supposed to be times r squared. Well, I know at this moment, r is 5. I'm going to take that 5 feet and square it. I'm supposed to multiply by dr dt. That's the thing I don't know. So I'm going to think of dr dt as my variable in this scenario. I'm going to try to isolate it. So I'm going to simplify both sides a little bit. 100 pi cubic feet per minute is equal to 100 pi square feet times dr dt. Well, it just turns out that if I divide both sides by 100 pi feet squared in order to isolate the dr dt, it's going to cancel out with 100 pi to give 1 foot per minute is my dr dt. So the answer to their question is at the time when the radius is 5 feet, the radius is increasing at a rate of 1 foot per minute. And just notice that those units should match. R is measured in feet, so the units in the numerator are feet. Time is measured in minutes, the units in the denominator are minutes, 1 foot per minute. All right, so to answer part B, we know the same thing that we knew last time, which is we know dv dt. We now also know dr dt at the exact moment when r equals 5. That's what we found as the answer to part A. The thing we're looking for is the derivative of this, is the rate of change of the surface area, which I'm going to call capital S, you can call it whatever you like, at the exact moment when the radius is 5. So do I know, let's see, right, do I know an equation I can write that relates surface area to either one of these. Well, I do know a formula for the surface area of of a sphere. Surface area, I'm gonna cos S is 4 pi r squared. Don't feel bad if you can't squeeze the v in. You just need an equation that relates this variable, s, whose derivative we care about, to something that you already know. So now I can take the derivative of both sides, so ds dt is going to be, the 2 comes down, so 8 pi r. But that was the derivative with respect to r. I need the derivative with respect to time, which means I'm going to multiply by dr dt. That's the implicit differentiation. That's what makes this a related rates problem. As a t. So now that I have an equation that relates ds dt with stuff I already know, I'm going to freeze the picture. I'm going to replace what I need to know. So ds dt is going to be 8 times pi times, no, this is ds dt at the exact moment when r equals 5. Equals 5. So I had 8 pi r times dr dt. It's going to be 8 times pi times 5 times, in part A, we found out that dr dt at that exact moment was 1. So that's 40 pi. ds dt is 40 pi. I have two choices for the units. I could go back and put units on each of these things and take them along with me, or I can look at this expression that I was supposed to find. That's the rate of change of an area with respect to time. Well, in a place where I have radius measured in feet and time measured in minutes, I know that area is going to be measured in feet squared, and time again measured in minutes is going to be feet squared per minute. Final answer.